Okay, picture this for a second. Think about the sheer, high-stakes reality of a heavy equipment rollaway. You've got a 10-ton piece of machinery just sitting there on a grade. Now, what happens if that truck's parking brake suddenly decides to fail? Well, without an ultimate physical backup plan in place, gravity just takes over, and that literal mountain of steel becomes a totally unstoppable force.
Welcome to this explainer. Today, we are diving into a seemingly simple tool that carries the weight of the world, literally. We're going to explore exactly why wheel chocks prevent accidents, looking at how engineering and physics combine to save lives, protect expensive equipment, and stop catastrophic accidents before they ever happen on the job site. Here's our roadmap for today. We're going to cover beyond the parking brake, the anatomy of a wheel chock, the physics of placement, slopes and shifting weights, and finally, adapting to ground conditions. Let's get into it.
All right, kicking things off with Section 1, Beyond the Parking Brake. This really establishes our baseline of safety.
So, what exactly is the hero of our story here? A wheel chock is basically a wedge-shaped safety device placed firmly against a tire. But it's way more than just a block of material. It serves as a physical, totally unyielding barrier against unintended movement. Think of it as this absolutely crucial extra layer of protection that works in tandem with the chassis' parking brake. In fact, OSHA regulations actually require wheel chocks or equivalent restraints in a ton of loading, unloading, and parking situations. Why? Because a mechanical brake alone just isn't enough when you're handling massive loads.
Moving right along to Section 2, Anatomy of a Wheel Chock, or Engineering the Barrier.
You know, not all chocks are created equal. Just look at this stark contrast. Engineered chocks are specifically designed to maximize contact with the tire. They've got a wide, stable base to prevent slipping, and they're built to resist massive crushing forces. On the flip side, and believe it or not, people actually do this, folks will try to use makeshift materials like scrap lumber, concrete blocks, or even just rocks they found nearby. This creates a catastrophic false sense of security. They aren't designed for the job, and they will shift, crack, crumble, or just completely fail without a single second of warning.
And that brings us to the golden rule of sizing. The larger the tire, the larger the chock has to be. It sounds like total common sense, right? But it gets overlooked all the time. Chocks have to be matched not only to the tire size, but also to the gross vehicle weight rating of the equipment. Look, if you use a chock that's too small for the job, that tire is going to roll right over the top of it like it wasn't even there.
Okay, Section 3, the physics of placement. Let's look at the geometry of safety.
The best engineered chock in the world is totally useless if you get the physics of its placement wrong. Here are the exact procedural mechanics you need to nail down every time. First, seat the chock firmly against both the tire and the ground. Second, ensure there is absolutely zero gap. I can't stress this enough. Zero gap is vital. Even a tiny space lets a heavy tire gain dangerous momentum before it ever even touches the chock, which dramatically reduces your stopping power. Third, center it straight against the tire tread so you maximize contact and stability.
So how do we actually apply this geometry when we're on an incline? Well, if your vehicle is facing uphill, the rules dictate that you place the chock on the downhill side of the tires located on the lowest axle. Those downhill tires carry the greatest responsibility for preventing movement, so they are the ones that require your primary attention.
And the flip side of this is brilliantly simple. If you're facing downhill, the procedure shifts a bit. First things first, you've got to center the steering wheels straight ahead. Then, you place chocks on both sides of the downhill tires. By pinning the wheel this way, the chocks act together to lock it in and prevent movement in either forward or reverse directions.
Now, what if you are on perfectly level ground? You might be thinking, hey, I don't really need them here. But you absolutely do. On level ground or on side-to-side slopes, you place a chock on both sides of the same rear tire. Oh, and here is a fantastic safety pro tip from the source material. If you're working near a roadway, always chock the curbside tire first. That way, you can secure the vehicle without ever exposing yourself to passing traffic. It's one of those small details that literally saves lives.
Let's transition over to Section 4, Slopes and Shifting Weights. This is where we confront the dynamic dangers out there.
The crucial thing to understand here is your limits. As a general rule, the steeper the slope, the larger and more robust your chock needs to be. A lot of standard wheel chocks are actually only rated for grades up to 5 degrees. Anything steeper than that, you're going to need larger chocks. But keep in mind, a chock never ever replaces proper equipment setup, leveling procedures, or adhering to the manufacturer's strict slope limitations.
Now, I want to pose a question that highlights a really dangerous myth you see on job sites all the time. If outriggers are deployed and they happen to lift the tires completely off the ground, which we see constantly with mobile cranes, do you still actually need wheel chocks?
The answer is a massive, resounding yes. Just because the tires are suspended does not eliminate the need for anchoring. Why? Because the equipment's weight distribution actively changes during operation. Think about it, as a crane or aerial device rotates, that incredibly heavy load shifts from one side of the machine to the other. That shifting weight changes everything, making chocks on the downhill side completely essential to maximize your stability, even when those outriggers are fully deployed.
Let's move to our final section, Section 5, Adapting to Ground Conditions, specifically looking at soft earth and ice.
Really poor ground conditions can completely undermine all that physics we just talked about. Look at how environmental hazards just change the game. On soft ground, all that massive weight basically just pushes the chocks straight down into the dirt. The fix? You need a chock with a significantly larger base to spread that weight out. On frozen or slick surfaces, your parking brake is way less effective, and the chocks themselves can lose their grip and just slide like a sled. In those kinds of adverse conditions, you've got to add extra precautions to actively anchor the vehicle.
I want to quickly highlight the vulnerability of trailers here. The rule is incredibly simple. Unhooked trailers should always be chocked. You must safely chock the trailer tire before you attach it, before you unhook it, and especially when you are loading or unloading equipment from it. You have to treat a trailer with the exact same respect and follow the exact same rules as you would for a tow vehicle.
All right, let's summarize the stakes by recapping our fundamental core rules. Creating a defense in depth takes discipline. Always use an approved, correctly sized chock. No makeshift lumber allowed. Use more than 2 chocks if your slope or ground conditions demand it. Always chock the downhill side of the downhill tires on both sides of the truck. And, just like we mentioned, chock your trailers using those exact same rules.
To wrap up this explainer, I really want to leave you with this powerful thought straight from our source material. Placing the right chocks in the right place will help protect you and the equipment from the unexpected. Preparation is your ultimate fail-safe, right? It is literally the physical barrier between a normal day on the job and a total catastrophe. So I'll leave you with this to chew on. Next time you walk past a massive 10-ton piece of equipment just idling on a job site, ask yourself, what is actually stopping that mountain of steel from moving?